Hi, this is Math 2115, Remote Delivery, for April 28th, 2020, and the topic is planar graphs and such. Make sure you use keys like this and you know what to do. Let's open with a little story. It actually is a very classical story. You have three houses in a small village that all need to be supplied with water, gas, and electricity. Can you make all the connections between the houses and supplies without having any two cables crossing? And you are drawing this on a piece of paper. So hit pause, try it, and let's see how you did. Well, I'm sure you failed because actually it is impossible. That's one of the reasons that they bury these utilities at different depths, because they can't accomplish this in the same plane. You did fine until you had to draw the last interconnection, and then you could not do it. We'll return to why this is true later, but we need to set up some machinery first. So we say a graph is planar if it can be drawn in the plane without its edges crossing. This does have applications to printed circuit boards where you don't want lines to cross because of the interference. And another definition is, if a connected planar graph is drawn in the plane is divided into contiguous regions called faces. A face is characterized by the cycle that forms its boundary. A picture is usually worth 1,000 words, and this one is worth at least that. We do have one face that is outside of the entire graph. That is by definition. But inside you can see that we have 6 other faces, and you see what they are as in terms of being contiguous. They're bounded by the edges, and we have 6 vertices in this graph. And this is a planar graph because we could draw it on this piece of paper, and we see that this equation ends up being 2. This is going to be called one of Eulers' equations. Euler has many such equations. Let's go back to the utilities then, and previously we called the graph associated with the utilities problem K33. So we're going to prove that this is not planar, but we're going to do it by contradiction, so we suppose it is planar. Now that means that every cycle has at least 4 edges, and that means that each face is bounded by at least 4 edges. Thus, the number of edges that bounds faces is at least 4 times the number of faces. Now, in a planar graph, again, we're assuming that each edge belongs to at most 2 cycles bounding each other. Therefore, 2e is bigger than or equal to 4f. Now, we're assuming that it is planar, so that means Euler's formula holds. We'll prove that later, but that means that 2e is bigger than 4, and this is what the formula is for f. So if we look at the figure up here, count the edges and vertices, we see that that tells us that 18 is bigger than or equal to 20. That's a contradiction, therefore it is not a planar graph. We also had a name for this graph. Well, this is the complete graph with 5 vertices. We called it K5. K5 is also not planar. I'm asking you to show that. Why don't you hit pause and we'll see how you do. Let's see how you do. First, we note that, and again we are going to assume that it is planar. So first we note that if we do have a simple connected planar graph, that the number of edges is less than or equal to 3 times the vertices minus 6. Now, we have to think through that. Since every cycle has at least 3 edges here, each face is bounded by at least 3 edges. Thus, the number of edges that bound faces is at least 3 times the number of faces. In a planar graph, each edge belongs to at most 2 bounding cycles. You need to think about these things. But therefore that means that 2 times the number of edges is bigger than or equal to 3 times the number of faces, but we're assuming that this is planar, and that means Euler's formula holds, so the faces is equal to this. We do some algebra and we solve, and we get 3b minus 6 is bigger than or equal to e. Now, so that's true for any planar graph. If we assume this was in planar, this is planar. We have 10 edges and 5 vertices, But that tells me that 9 is less than 10. That is a contradiction. So you see, this is also not planar. Now here's a couple of exercises that just show that each graph is planar by redrawing it so that no edges cross. Give these a go, and we'll see how you did. You could have drawn something different than what we come up with, but these are examples where you could redraw those. Again, these graphs are isomorphic, one with another. Okay, returning back to the main line then. So obviously if a graph contains either this one or this one as a subgraph, it can't be planar because I can't draw these within a plane. But the converse is not true. However, as so often happens in math, if we introduce a new concept, and this is going to be called homeomorphic graphs, we're going to define that in a bit, we can obtain a true statement similar to the converse. And in fact, this is an elegant, very high-powered theorem. But we need a definition first. So if a graph has a vertex v of degree 2 and edges connecting with that, and it's not a loop, we say that the edges are in series. And then we perform what we call a series reduction. Consists of deleting the vertex that's in series with the other two and replaces it just by a single edge. The resulting graph, G prime, is said to be obtained from G by a series reduction. By convention, G is said to be obtainable from itself by a series reduction. That means we're going to be able to call this the homeomorphic graphs. We're going to be able to call those an equivalence relationship in a bit. Okay, so here you can see that these three vertices are in series, so if we remove it, we get G prime. So G prime is obtained from G by the series reduction. Here's another example. We say that, we can say that G1 and G2 are homeomorphic since they can both be reduced to G prime by series reduction. You see we reduce that, and we reduce that, and we get this is G prime. And as I said, it is a equivalence relationship. I should have defined that, and I don't know if I did that clearly or not. But anyway, here's a couple more problems. Here you're supposed to show that this graph is not planar. Let's pause and see how you do. Well, if you remove those links, you obtain a graph that is homeomorphic to, and this is the one we call K33. So this is not planar. Now here is Crotonski's theorem, and it says that a graph G is planar if and only if G does not contain a subgraph homeomorphic to either of those two subgraphs that we've talked about. Now this really does give an elegant characterization, and the proof of this is beyond the scope of this course, but it's an elegant characterization of planar graphs, but it's not an efficient algorithm. But there are algorithms that other people have studied this much more recently, and these algorithms are big O of n. Now, here's an example of how much work it is to show that they're not planar using the theorem. So what you do is you eliminate edges to form a subgraph, and then you eliminate more edges to find a subgraph that is homeomorphic to the one that we had before, and you see that this is has a subgraph that is homeomorphic to, that is K33. Another set of problems where you're supposed to determine whether each graph is planar. So redraw it and otherwise find a subgraph homeomorphic to either this one or this one. Let's pause and see how you do. Let's see how you did. This number 7, the first one is planar. You could redraw it this way. The next one is not planar, and again we have something that is homeomorphic to K33. Now we come at long last to Eulers' formula. We've used this many times. It is an important formula in graph theory, but what we're going to do is we're now going to prove it, and we're going to prove it by induction on the number of edges. So if G is a connected planar graph with E edges, V vertices, and F faces, then F is equal to E minus V plus 2. So we use induction on the number of edges. So suppose there's only one edge, then there's only two possible graphs, this one and this one. In either case, the formula holds, and so we're finished with E equal 1. Now, we're going to suppose that the formula holds for connected planar graphs with n edges, and G is a graph with, and now we're increasing this by 1. This is the induction step. We're moving ahead. We're going to take one of these. Now, we know the formula does hold for n edges. So suppose G contains no cycles, and we'll consider the other case where it contains a cycle. So we pick a vertex V, and we trace a path starting at V. Since it's cycle-free, every time we trace an edge, we arrive at a new vertex. Eventually, we'll have vertex A with degree 1 that we cannot leave, and that's shown down here in this figure here. There's an example of hitting vertex A. We delete A and the edge incidence on it from the graph. The resulting graph G prime has n edges, hence by the induction hypothesis, the formula, Euler's formula, holds for G prime. Since G has only one more edge, one more vertex, and the same number of faces, it follows that it also holds for G. But now suppose there is a cycle. Well, we let X be an edge in the cycle, and see that this is the example. Now X is part of a boundary for two faces. This time we delete the edge X, but no vertices to obtain the graph G prime. Again, G prime has n edges, hence the induction hypothesis holds for G prime. Since G has only one more face than G prime, and one more edge than G prime, and the same number of vertices as G prime, it follows it holds for this as well. It would be wrong if I didn't mention the map coloring problem. In mathematics, the four-color theorem, or the four-color map theorem, states that given a separation of a plane in contiguous regions, like on a map, that no more than 4 colors are required to color the region of the map, so that no two adjacent regions have the same color. And adjacent means that two regions share a common boundary, not merely a corner where they meet. And there is a state here somewhere, I think it's the state right here, where they all meet in a point. This was a very famous theorem. The proof for 5 colors was done in the 1800s, but this wasn't proved until actually very recently. It was the first major theorem to be proved using a computer, and it was really quite controversial for that, because the computer assisted, because it was infeasible for a human to check all of these possibilities by hand. And this talks a little bit more about some of the details of the proof on this side. Now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other.